In this video, we'll now jump into the big application of differential equations, which is modeling. So modeling is the big way that differential equations show up outside of math classes. They show up pretty much everywhere. Any kind of science, engineering, physics, all of those fields use differential equations to help them model situations. And it's that reason why this class exists, to help prepare future scientists and engineers to be able to use these equations to help them model and solve problems. So if you want to model or calculate information about anything, about stuff that's changing or moving, you need differential equations. This goes from anything to fluid flow in a pipe, pollutant concentration in a lake, price fluctuation, disease modeling. All these are really best situated in the language of differential equations. And the point about modeling is learning how to speak that language and be able to talk about these different concepts using these equations and being able to set these problems up so then you can solve them with the method that we cover in this course. And that's what we need to put together to be able to do. The general step underlies most of the models that we will see that are used pretty much anywhere is the accumulation equation. Depending on your field, this could be a mass balance or an energy balance, or depending on what class, a bunch of other balance type equations. But the idea is all really the same. And it really comes down to the following. The overall rate of change of some quantity is the rate it is being added to, and minus the rate being taken away. The way I normally picture this or think about this, right, the total change, or net change depending on how you're talking about it, is the rate in minus the rate out. Basically, take all the factors that come together to add to this quantity throughout your model, add those together, those become the rate in. This could be many factors. It doesn't have to be just one thing, but however many things go together to add in, put all those together. Take all the things are taking away from this quantity. That goes into the rate out. This could also be many factors as well. And put those together to determine the total change. This over here is usually where the derivative comes into play, because if I want to look at the net change or the rate of change of some quantity, that is the derivative. And then the rate in and rate out can depend on many different factors, how things are changing, what's going on in the problem. But this part's where like the physical system will come into play and how it makes this model. As a sort of basic example, if I have a cup that's filling up with water, I can model the volume of water in a tank with a, say, dV dt is the total net change of volume, and this would equal all the different factors coming into play to add and subtract water from this cup or this tank, whatever it may be. So for instance, if there are two different hoses putting water in at a certain rate, I would then have, say, hose 1 plus hose 2. And if you had someone trying to bail water out of it for some reason, that would be a negative factor. It's pulling away water at a certain rate. So that becomes how much someone's bailing out the water. And combining those together gives me the overall rate of change, which I can then solve to figure out how this volume changes over time. Now, in this case, these are probably all constant numbers, but you get more involved equations when these different quantities also depend on the volume of the water. Other parameters in the problem can cause these to be more complicated and give you more involved differential equations that you need to solve, which is like the one we have here. So if I have v being the velocity of an object that's being dropped, we know it falls and will accelerate downward due to gravity. We have that acceleration of 9.8 meters per second squared. That's going to pull it down. Or there's also drag on the object, which will reduce the velocity at a rate that is 0.1 times the square of the velocity. So what do we have for a differential equation here? Well, our velocity is the thing that's changing. So we want to say our total net change is our derivative velocity in time. How are we adding to the velocity? Well, we are adding to it with gravity. So we are adding to the velocity at 9.8 meters per second squared. And that's the only factor that's actually adding to the velocity. How are we taking away from the velocity? We're taking away via drag, which is given by 0.1 inverse meters times the square of the velocity. So times this v squared. This v is the same as the v that's in my equation itself. So that there gives me a differential equation that I could try to solve. The equation says that my net rate of change is the rate in, how I'm adding to that quantity, minus the rate out, how I'm taking away from it. And that's how most of these models end up coming together. You're looking at some quantity, something, you want to figure out how it's changing. Well, there are certain factors that add to it and make it bigger. Those come with plus signs. There are certain factors that subtract and take it away. They come in with minus signs. Put those all together gives you an overall equation for how this thing will change in time. Then to get the actual solution, we then want to solve the differential equation to see what's going on with this physical quantity. In this case, for instance, we would see that there is a terminal velocity that will come out of a place where the object stops accelerating downward because the drag cancels out acceleration due to gravity. Now we can get just by taking this equation and trying to solve it to see what kind of result we get. There are a lot more complicated models, but this just gives an idea of how most of those models are built, how they're formed, and then how you could write your models for your own types of things and learn to then interpret and solve these equations from these models.